हर रोज़ मेरा खुद से उलझना, कहीं ये बगावत तो नहीं। दिल परेशान है तेरी मासूमियत से, कहीं ये बनावट तो नहीं। वीडियो बनाई है ऐसे विषय पर जिसकी जनता कम है। जानते हैं कुछ खास नहीं चलेगी, फिर भी न जाने क्यों ज़मीर में दम है। बातें हो रही थी उनकी, कब से तारीख याद तो नहीं। आज फिर से आयनाइजेशन चैम्बर पर वीडियो बनाई है, कहीं ये बनावट उन्हीं की तो नहीं। So in today's video we'll be talking about the design of DC ion chambers. The ion chambers used in direct current mode. So we need to collect the current in case of ionization chambers. Talking about the cations, they move towards the cathode, and the negative charges, they will move towards the anode. So negative charges, as you know, they can either be electrons or anions. Now what is the difference if we have current because of electrons and anions? You know, recombination can be between anion and cation or electron and cation. Recombination between these two is more probable as compared to the recombination between the electron and cation, which means that if there is formation of anion, recombination will be more dominating in this case. Secondly, talking about the diffusion losses. This equation we have talked about in our previous video. Links are in the description box, you can check it out. So because of the diffusion, the loss in the ionization current is governed by this equation. We have talked about all these parameters. Now talking about this epsilon, which is the ratio of average energy of the charge carrier in the presence of electric field to that without the presence of electric field. You know, for the case of ions, this factor is not greater than unity, which means that ions, which can be cations or anions. So ions, they do not gain much energy even if the electric field is imposed, and this factor is of several hundreds for the case of electrons, which means that diffusion losses because of the formation of anions will be much less as compared to the diffusion losses in current because of the electrons. So this losses for the case of anions is less and recombination is more, and both these factors, they are eventually decreasing your measured current. So this is the main difference between these two. Now talking about the fill gas, which type of gas you need to use in your ionization chamber. Any gas can be used, including those having high electron attachment. That means gases which favor electron attachment, like oxygen or other gases in which anions are readily formed, they can also be used in your ionization chambers as the fill gas. Secondly, talking about the most common choice which is preferred in an ionization chamber is that of air. Negative ions are readily formed in air. Also, this is used in all those applications of ionization chamber in which your aim is to measure gamma ray exposures. If you want to increase the ionization density in a given volume, you want the number of ion pairs to be more. In that case, you need to use denser gases. Argon being denser as compared to air, this will be preferred if your aim is to increase the ionization density. Also, the gas pressure that needs to be maintained is 1 atmosphere. And if you want to increase the sensitivity of your ionization chamber, that means that you need to increase the amount of ionization current that you are getting from the chamber. You have to increase the pressure. So pressure कैसे increase करते हैं, we'll be talking about this aspect in our subsequent videos. For now, you need to know that increasing sensitivity means you have to increase the current obtained from the ionization chamber, and for this you will eventually increase the wall thickness. We'll be talking about these aspects later on. Okay, so now I'm talking about the geometry. Which type of geometry should be preferred in an ionization chamber? The answer to this question depends upon the application for which you want to utilize this chamber. First, talking about the parallel plate geometry, you can have cathode and anode. Parallel planar electrodes, they are placed parallel to one another. Cathode is the electrode at negative potential and anode is the electrode at positive potential. So this will be connected like this. These are parallel plates, and the electric field, the expression for electric field that you will be obtaining for such a geometry is this. So electric field is this V, this potential of the battery, and divided by this D, which is the distance between the two plates, distance between the cathode and anode. Okay, so you know that this distance will be constant. If you fix the geometry, this distance will get fixed, and this voltage is also fixed that you are applying. This is the applied voltage, which means that for the case of parallel plate geometry, you will be getting uniform electric field between the electrodes. So if your application demands or requires uniform electric field between the electrodes, you will go for this. Secondly, talking about the cylindrical geometry. Cylindrical geometry in which this hollow cylinder will be acting as cathode. So you have grounded this, or you can maintain it at negative potential. Central wire, this will be the anode, and it will be maintained at positive potential. And in this case, the electric field at any point on the anode wire will be in radial direction. It will be emerging outwards in all direction. So it looks like this, and which means that the electric field in this case for the cylindrical geometry will be inversely proportional to the distance. So which means that as this R, as this distance will increase, as the distance from the anode wires, because this electrode, this anode is maintained at the positive potential. So electric field lines will emerge from this anode, from the points on the anode, and it will all be in the radial directions. So which means that as you move close to the anode wire, as you move closer to the anode wire, the electric field strength will gradually increase, and moving far away from the anode wire will lead to a decrease in the electric field strength. So change in the geometry will also lead to a change in the electric field, the expression for electric field that you are getting. Depending upon the application for which you want to use your ionization chamber, you will be preferring one geometry over the other. So is there anything else that you require for this geometry or the design of ionization chamber? Well, one thing that we need to note over here is that if this was anode and this cylinder was cathode, and this is enclosed within this wire is enclosed within this cylinder, and we want to maintain these two things at different potentials, two electrodes at two different potentials. So one major requirement is that we need an insulator between the electrodes. So whatever the geometry may be, you need to separate your cathode from the anode with the help of an insulator. Because they both are at different potentials, you cannot connect them together. So if you talk about one side of this cylinder, you have cathode over here and this is the anode wire. So you are separating these two electrodes with the help of this black insulator. Talking about the ionization current, the typical ion current which is observed from an ionization chamber is of the order of 10 to the power minus 12 ampere or even less than that. So this means that current that you are getting is not much. If you want to measure this precisely, you cannot tolerate any additional current coming from any other place and adding on to it, so that the final result that you are getting is much greater than this. We do not want any other current except for this to be measured by this ammeter. But one thing is that you have already inserted insulator between the electrodes. You have used them, so which means that whether you want or not, some amount of leakage current, leakage through the insulators, you will be getting, which will be adding into this, so that your measured current will be more, and the result is that you will be getting ionization plus current due to leakage, and this comprises of unwanted component which you do not want your ammeter to measure. What to do then? So if you cannot eliminate something completely, you can always try to minimize it. If I cannot eliminate this, I can always try to minimize it. So you know that the order of ion current that you will be getting is of this 10 to the power minus 12, and if I want this to be below 1% of this ionization current, below 1%, so 1% of this 10 to the power minus 12 will be this minus 14 का order होगा. So I want my leakage current. I want my leakage current to be of this order. So that addition of this into this won't make much difference. And if my applied voltage is of 100 volts, applying Ohm's law, the amount of resistance that I'll be getting is of the order of 10 to the power 16 ohms. Now, this means that you have used an insulator, and because of this you are getting some leakage current. I cannot eliminate that leakage perfectly, so I tried to minimize it, and for this, in order to keep this leakage current below 1%, the resistance of the insulator that I will be requiring should be more than 10 to the power 16 ohms, which means that this limits the type of materials that can be used as insulators in my ionization chamber. Such high resistance values I need for my insulator. Second problem with your insulator is that presence of moisture or contaminants will eventually decrease this resistance. First of all, you require high resistance, and there are inevitable factors which are always decreasing this. So is there any other solution? Well, we have guard rings. So talking about the geometry of ionization chamber, if I talk about one side of this ionization chamber, you know that this is the cathode cylinder, and this was the anode, the wire, the axial wire. This is the anode, and I told you that you need an insulator between the electrodes. So this black is your insulator which is separating your cathode from the anode. See, both the ends, you can see this. Anode will be connected to the positive end of the battery, and this cathode will be connected to the negative end, and you have an ammeter which will be measuring your ionization current. So this is the simple construction that you know so far. Now the next aim was to eliminate this part. So we'll be focusing on this now. We want to minimize this, and I told you that we need guard rings for this. So guard rings are placed over here. So guard rings will be inserted like this, in such a way that insertion of a guard ring will divide this insulator into two parts on either side of this anode wire. So I had my complete insulator separating the electrodes over here, and in between this insulator I have inserted these guard rings. So I have one guard ring here, another guard ring here. So does that solve the problem? No, I need to make another connection over here. I will also be connecting these guard rings together like this, and further I will be connecting it to this positive end of the battery. So this is the equivalent circuit. I have drawn this complete ionization chamber over here. This is the cathode, this entire cathode, and you have insulators in which you have inserted your guard rings. This is acting as your anode. Anode is at your positive potential, cathode at negative potential, and you have replaced this ammeter with the resistance of the ammeter. So this is the equivalent circuit, and now you will be connecting these guard rings in the same way as you have done here. So this is like this. Let us observe how this connection will help us to get rid of this. We want to get rid of leakage current. So कोई चीज़ अगर हमारे रास्ते में आनी ही है तो कोई चीज़ अगर हमारी लाइफ में आनी ही है और हमें वो नहीं चाहिए, हम उसे नहीं रोक सकते, अपना रास्ता तो बदल सकते हैं. Similar thing I will be doing over here. I will be having current flowing through this circuit like this, and now I know I have a component of current going over here and another one going over here, such that this I will be sum of these two. I will eventually be sum of these two. Now you know that you have insulators. You have these insulators over here. These guard rings are conducting. They are made up of conducting material. So you have an unwanted component of current because of these insulators. So any sort of leakage from this insulator will be conducted by this guard ring into this, and you will have your direction to be like this. So This is your leakage current because of this insulator. Also you have insulator over here, so any leakage from here will be conducted by this guard ring into this. You will be having your leakage current in this direction over here. So this will eventually go from here, and this current will be because of leakage, I leakage. Also you have another current because of the ionization. You have radiations into this ionization chamber, and because of this you will be having your ionization current, and the path is again this. So which means that in addition to leakage you will be having ionization current at this point. You will be getting ionization and leakage. So which means that this I is nothing but I leakage plus I ionization. This current, if your current follows this path, you have high resistance insulators placed over here. So you have guard rings and your insulators placed over here, which means that this current which is going here, this is because of leakage. This is nothing but your leakage current, which means that if this was your total current and this is the leakage current, this is leakage current. Why? Because you have insulators placed over here. In this path you have no insulator. The resistance that the current will be observing is only because of the resistance of the ammeter, which can be kept very small. So this current will essentially be the current because of the ionization. So the current because of the ionization will be measured by the ammeter. Now what have you done here? By connecting the circuit with the help of guard rings like this, you have changed the path of the leakage current. You have changed the path of the current that you did not want your ammeter to measure. So if this is IL1, this is IL2, two leakage current, your I leakage will be the sum of these two, and you have changed the path of your leakage current. So this is why guard rings are essential. You have high resistance insulators over here, which means that voltage drop across this will be much more as compared to the voltage drop across the ammeter, because the resistance of this ammeter can be kept very small. Higher the resistance, more voltage drop, lesser is the amount of current. So let us now wind up this video with a brief discussion upon the materials that can be used as insulators. Well, it all depends upon the application for which you are using your ionization chamber. If your application requires the use of low radiation fields, for that case you can use synthetic plastics as your material for insulators. And apart from this, care should be taken that these materials should be as smooth as possible, free of any defects, so as to minimize moisture absorption, because that will eventually lead to a decrease in the value of resistance that you do not want. Next is where your ionization chambers are used for high radiation fields. In that case, your synthetic plastics will eventually lose their insulation properties because they cannot withstand such high radiation damage. In that case, you can use inorganic materials such as ceramics as your insulators, which will have much higher resistance to radiation damage as compared to plastics.